Good afternoon. I am Kyung-ho Kim from Hansong University. Today I'm gonna give a presentation about face light. The face light is an improved implementation of a face, which is on another AES optimized implementation that was introduced in chess at 2018. The face uses lookup table that are too large for low-end microcontroller. So we have reduced the size of lookup table and can be even used in 8-bit microcontroller. Also, we have removed the need to update the lookup table. The presentation goes as follows. First, we will introduce some of the background knowledge in order to help you understand our work. Next, we will explain the face method that was introduced in chess. Then we will introduce our work, face light, and lastly we will explain our contribution and our future work plan. First, introduction. The AES worldwide use block cipher, which stands for Advanced Encryption Standard, and the algorithm process is shown on the right side. The AES has various modes such as ECB, GCM, and counter, and so on, depending on the method of encryption and decryption. Today, we are gonna take a look at the AES counter mode. The counter mode has 128 bits of initial vector, which consists of 96 bits of nonce value and 32 bits of counter value, which are used as the input value in the encryption process. The nonce value is fixed and the counter value increased by 1 on each block. Due to this counter mode's feature, the processor of each block is independent to another block. This makes it possible to do a parallel processing and perform a faster encryption. Nowadays, one of the most important aspects when implementing a cipher algorithm is to have a countermeasure against side channel attack. The side channel attack is any attack based on additional information gained from the implementation of a computer system during algorithm operation. The most well-known attack is the power analysis attack, such as simple power analysis, differential power analysis, and correlation power analysis. In order to counter the side channel attack, a lot of research has been going on, and one of the most popular methods is masking technique. Masking technique involves implementing unnecessarily operation during the encryption in order to disturb from analyzing the power of the original encryption process. We have applied the masking technique with reference to the published masking technique and optimized according to our law and environment. Now, we will take a look at the face, which is the technique we referenced. The face utilizes the fact that only the last byte of the initial vector changes according to the counter value, which increased by 1 on each block. The rest value of the initial vector will remain same until some point. They make a lookup table with the unchanged values of the initial vector except the last 1 byte and will use it in future block operation. The size of the table will be 5 kilobytes and needs to be updated on certain periods. Now, I will explain why the table needs to be updated on certain periods. The whole process of the face block operation goes as follows. If we take a look at the screen above, we can see that except for the last byte as 15, the rest of the bytes remain the same from the first block to 255th block. In other words, during the encryption process, the uncolored part here remains the same until the round 2. This part can be stored as a lookup table in order to reduce the calculation. And if you look at the screen below, a carry occurs on S15, affecting on the S13's values. So we can see this carry also affects the other values of the block operation process. So it needs to update the lookup table. In round 0, except the last column, which contains the last byte of the counter value, the rest of the value, which are these 3 columns, will be repeated in the block operation. So this value will remain same until the counter value increased until 2 to the 32nd power and can be reused until so. After the 2 to the 32nd power block, the carry occur on S11, thus need to make an update on lookup table. In round 1, same technique can be applied as round 0, since except for the first column, which gets affected by the counter value, the rest of the value can be reused here. So again, we can create the lookup table like we did in round 0. This method of utilizing a lookup table can be used until round 2's shift rows, which the software can be optimized while using 5 kilobyte lookup table. However, the technique of the face has some limitation for use on 8-bit processor. First, the size of the lookup table can be a problem. Most of the low-end microcontroller has memory size of 2 to 4 kilobyte, which is not enough to contain 5 kilobyte lookup table. Second, the face requires the lookup table to be updated in each period, which leads to additional computation time. Now, our work, the face light, was able to resolve the aforementioned limitations. We have selected Arduino Uno board with AVR 8-bit processor as a target board. And Atmega 3 to 8 chips hardware spec is as follows. Our work, the face light, is an optimized implementation based on the face. Face light resolves the limitation of the face, which are the size of the lookup table and the requirement of updating the table. By doing so, our work became suitable to run even on the low power processor. Our work don't store the repeated value as the face did. Instead, we store the value that gets changed by the counter value and make it as a lookup table. This makes us possible to skip 3 rounds while referencing the 4 kilobyte lookup table only once. Also, the lookup table don't need to update, so we can utilize various memories such as flash memory instead of SRAM, which used quite a lot of computation resources. It can be used on any processor of 8 bits or above and can improve the performance a lot by merging the face mechanism with the face light. We call it extended face. And we have rearranged the 32 bits of counter value of the initial vector into the front of the vector here. If we take a look at the screen above, we can see that the counter value S3 spread throughout the round 0 to round 2 like it did in the face. In a situation like this, we can find some interesting feature about the counter value. If we paint the counter byte, we can see which counter bytes affect which value throughout the encryption process. If we take a look at the S0, this red value, we can see that the value only affects other 4 bytes since before the mixed column operation in round 2 here, and which only get affected by S0, S1. This is same with S1, S2, and S3. So we have made a lookup table storing these specific 4 bytes which only get affected by S0, 1, 2, and 3. Thus, we can omit the process since before the mixed column operation in round 2. We will take a look at the encryption process with some real value example. If we take a look at the red part of the counter value, we can see that the value spread throughout the rounds. Changes in the last value of the counter value will only affect the red part, not the other. So, since before the mixed column operation in round 2, we can see that only the 4 bytes will be affected by the changes of the last bytes of the counter value. This will remain same until the counter value reaches 255. So we can make a pre-calculated lookup table according to the last bytes of the counter value. And since it affects 4 bytes until 256 times, so we will need 1 kilobyte lookup table. So no matter what this value becomes, we can reference the 1 kilobyte lookup table and find the corresponding values. As we can see, the next byte of the counter value also only affects the 4 specific bytes. We can also make a lookup table for these 4 bytes. And this result, the rest bytes goes the same way. So each of the counter bytes has a 1 kilobyte of the lookup table, and the total number of counter bytes is 4, so the total size of required lookup table is 4 kilobytes. Also, the lookup table holds every values corresponding to the counter values change, so the lookup table does not require the update. In conclusion, since we have all the value from round 0 to round 2 as a lookup table, since before the mixed column operation, we can omit this process. Also, our work, the face light, can omit more process by merging it with the face. If you take a look at the screen above, we can see the process of the face. If you take a look at the S15, the counter value, we can see the S15 affect this first column through shift rows and mixed column operation. It means that if the S15 changes, these first columns are also change. Now, if we apply our face light process from the round 2, we can utilize the lookup table up to the shift rows process in round 3. In order to explain the extended face a little bit more, we need to take a look at the screen. Here is the whole process of face from round 0 to round 2, and here we have the whole process of the face light from round 0 to round 2. Now, If we take a look at the first column of the round 2 in phase, we can see that the first column got affected by the counter value as 15. Now, in the phase light, the first column of the round 0 is the counter value, since we have rearranged the initial vector to have the counter value in front, while the phase has the counter value in the back, like this part. So if we take this fact in consideration, we can put the round 0 of the phase light as the round 2 of the phase and extend the whole process. This will extend the effect the S15 has till the round 3 shift rows operation. In conclusion, we have used the phase and the phase light to extend the use of the lookup table, thus omitting even more rounds. Now, we will showcase our work's benchmark. If you take a look at the chart here, this is the clock cycle of the optimized standard AES, which is around 2500. Now our work here has the clock cycle of 2200, and if we can take a look at the cycle of the extended phase, we can see the clock cycle has decreased to 1967, which is 22% faster than the standard optimized AES. Also, no additional lookup table update time is required. And we will now compare our work, the phase light, with the phase. The phase cannot be applied to the 8-bit low power processor due to its limitation with the lookup table size. However, the phase light can be used on 8-bit processor since it used a 4 kilobyte lookup table and does not require a table update. So this makes the phase light to support on constant timing. In addition, the phase light method can be expanded merging with the phase until the round 3. This figure is a correlation chart and a graph showing the result of CPA on the AES and our work phase light using side channel analysis device Chip Whisperer. As we can see, the AES without the masking technique was exposed of its correlation of the secret key value. However, our masked phase light was able to keep the correlation of the key value low enough to be not exposed. If we compare our masked phase light to the other lightweight cryptography such as Lia, we can see it is much faster than masked Lia. This is due to the fact that the Lia used ARX operation, which decreased the performance dramatically when applying the masking technique because of its complex arithmetic Boolean operation. However, the AES uses SPN operation, which does not use arithmetic Boolean operation, thus able to maintain decent performance even masking technique is used. The masked phase light shows around 6200 clock cycle, which is quite faster than the other masked lightweight cryptography and even the masked AES. Lastly, we will discuss about our contribution and our future plan. Our contribution is that we have effectively implemented a AES counter on a low power processor. Also, our work is more expandable than the face, and it is more difficult to predict attack points since it runs on a constant timing by not having to update a table. Also, we have applied it masking technique to our work in order to counter the side channel attack, which is a must have standard for modern cryptography. Lastly, as we saw in previous page, the clock cycle of the phase light was around 2200. Considering the LIA lightweight cryptography has a clock cycle of 2600, it can be said that the phase light can be also considered to be lightweight cryptography. And we will discuss about our future work. We are planning to implement an optimized AES on various other platforms like 16-bit MSP and so on. Also, we are going to optimize some of the domestic cryptography with our works method, such as pre-computation of the lookup table using masking technique and optimization of the software. Lastly, we are planning to apply our proposal methods to other AES modes such as GCM and such. Thank you for listening to my presentation.